All right, ladies and gentlemen. Okay, good morning to you guys. Let's see who's here. Who do we have at home here today? We have, looks like it's New Yin. My mouse is not working, so. Luke, good morning. Layla, good morning. Paula, good morning. So good morning to everybody here. And we're going to take a look here. Let's go back to this website and see if we can scroll down. No, we don't want to do that. Let's go to Math 262. I think there's some online transition. And integration by partial fraction decomposition here. Alrighty, so here I have some notes for you guys there. That's what we want to talk about. And as you guys can see, you're going to integrate rational functions, right? So if you look at that there, let's see if we can make that bigger. All right, that looks pretty good. We're going to integrate some rational functions. So as you guys can see here, for example, without the mouse, it's a little odd. There we go. We're going to have to look at, for partial fraction decomposition, we're going to have to look at cases for the denominator, right? We're going to look at that situation. So this goes back to Math 260, partial fraction decomposition. This goes back to pre-calculus, those courses. That's where you study partial fraction decomposition. So you have cases. You have linear factors, and it's really called distinct linear factors, different linear factors. You have repeat linear factors. Case 3 quadratic factors, and then case 4 really repeat quadratic factors, and that's pretty far. That's as far as it goes, ladies and gentlemen. So that's what we'll be looking at this morning. So those cases, a summary of what we're doing is here. And so let's kind of take a look at some of those cases here, right? So this is a review of partial fraction decomposition, and maybe look at that. Let's get rid of this here. Okay, that was from last night. And here we go, ladies and gentlemen. Okay, let's take a look here. So let me share with you guys what I'm talking about with these cases here. You're going to integrate. We have x over, I have x plus 4 times 2x minus 1 dx. Okay, so you're going to focus on the denominator down here. Okay, now what you see here in the denominator is what we call distinct. So distinct means different. Distinct linear factors. So distinct linear factors, remember, a linear equation is anything that looks like this, mx plus b, right? And that's what they're talking about here. You have different linear factors, okay? Now, partial fraction decomposition, again, what we say here, that's when you write a rational function, this is a rational function, as a sum and differences of two or more linear, simpler rational functions. So let me go back here. So we're going to take this rational function, we're going to write this as sum and differences of simpler linear or simple rational functions like we've seen last time. So what I'm going to do here is I'm going to take that rational function here. Here's what I mean by that. You got that rational function x plus 4, 2x minus 1. And what we do by setting this up in the first place is we take that rational function and we write it as a over, here's my first term, down here, right? A over the x plus 4, and a is a constant. And then we write this as b over 2x minus 1. So if you guys remember that here. All right, so we have this rational written as a sum of two simpler rational functions here. And again, going to point out to you guys here, a and b, these numbers are constants. So they're just numbers. So the task really becomes to determine is what are the constants? What are the numbers? A and B. Okay, so let me do that here, and that's kind of where what you're looking for. Trying to find the numbers A and B, those constants. Now, excuse me, here's what I'm going to say. Here's what you guys can do. On the right side, for how you're going to try to find the constants on this right side, what you guys are going to do is you're going to do some algebra. Right? That term called algebra again. Meaning you're going to add two fractions. And if you guys remember, adding two fractions, you kind of have a shortcut algorithm, I would say. You know, the shortcut algorithm, it's going to be the following, if you guys remember. It's the cross multiplication for the numerator, and for the denominator, it's this, horizontal cross. So you got that BD, I'll say this is AD plus BC. So this is going to be something that we can do here in this case. This is what we want to do, some algebra here. All right, so if we do that, notice what that gives us. That gives us now A times 2x minus 1 plus B times x plus 4, doing that cross multiplication, doing the algebra. And that's x plus 4 times that 2x minus 1 here. Okay? So this is what the algebra that we just did right in here for what you have there. All right, so you're adding those things. Now, let's look at this logically. Here's some logic here. On the left side, what do you have? The left side, you have what? X over x plus 4 times 2x minus 1 becomes a times 2x minus 1 plus b times x plus 4, everything over x plus 4 times 2x minus 1. Right? This is the left side equal to the right side, what we're seeing here. We're going to use some logic. Now, here's what the logic I'm talking about. This denominator and this denominator are the same. So you have two fractions that are equal. Okay? And they have the same denominator. What that implies here, I'm going to want you guys to put this as a note. We're going to give you every detail here. That if you have a triangle over a square equals that, I'll put a heart, I guess. So people don't think that's 0, right? If you have this situation, same denominators, then what do you think that means? Do you guys know what that means? Yeah, it means your numerators must be the same. So it means right in here that this and this, these are equal. That's what that means. So you have x over this portion, they're going to be the same. Right? So this implies here x will equal a 2x minus 1 plus b times x plus 4. Okay? All right, ladies and gentlemen, this is in some ways, this is simply getting started. This again is what we call case 1 when you have what? Distinct. What does that word distinct mean? Different. Linear factors. We call this case 1. This is where you always start for partial fraction decomposition. Now, we're not done here because remember what you're trying to do. Remember what you're trying to do? Trying to find the values of the constants A and B. What do A and B have to be? Now, there's going to be two ways we can do this. In case you guys didn't know, there's two ways we can try this out. And you might say, well, what are the two ways, right? All right, so we're right here. So let me do a couple of things here. I'm going to do some algebra here. Right? We're going to distribute here. So these constants here, this means this is x. You get 2ax minus a plus bx plus 4b here. Okay, just by distributing. And what I'm going to do now is this is going to be here. We're going to have x equals 2a plus b. I'm going to get out this x term here. Okay, and then we're going to have plus maybe, I'm going to write it this way, 4b minus a. So let me kind of share with you what I just did here. I grouped my what? My x terms together. Is that right? Right, so I factored out like the x, and I got 2a plus b. And then these two terms here are just thought of as your constants. But I wrote it as 4b minus a because, you know, I can start this off with a positive number, not a negative number. Okay, so this is going to be the equation we use here. This is a couple of approaches. Now you might say, okay, where are you going with this, right? Well, let me say this here. If you guys look at this here, this equation is a very special equation here. I'm going to do something here. I'm going to say this is x plus 0. So I do this because logically the left side of your equation is the same as the right side. Is that true? These are equal. And then you have that constant 1. So that's 1 times x plus 0. So what this means here, I want you guys to see this here. What this means, if I can find the right colors, or any colors, whatever. The constants here, right, what do you guys think this means? This means 2ab, 2a plus that b. You know what that has to equal? 1, exactly. Good. Outstanding. And then that means also in green here, the 4b minus a has to be what number? 0. And maybe you might say, well, what does this mean? Well, here's a couple things. I guess I'm going to have to start with that negative after all. Okay? What you guys now have here is what we call two equations and two unknowns, right? Two equations, two unknowns. The unknowns are the constants a and b. So this is now, believe it or not, in some ways, you can say this is a beginning algebra system. This is a system of equations, right? So how did you guys solve system of equations? This is a 2x2 system. Do you guys remember how you solve those from beginning algebra? I think there's 3 ways. Right? You guys remember? How do you solve a system? 2 equations, 2 unknowns. Huh? What do they have here? I got my phone bugging me. Okay, let's think back. Math 115, beginning algebra, right? We have what we call the addition method. You have the substitution method, if you guys remember. And then you have graphing. And, my mouse is not working. I don't know if I'm hoping that it's not broken. I'm hoping it's just that it needs to be charged, although usually it tells you it needs to be charged. And I didn't have the cable with me today. So, you know, otherwise I go to my website and I'd show you guys. Well, maybe I should try. You guys want to see that? Let's try that. Let's go to the website. I'll try to show you guys here. Go all the way back here. Back here. Got to go to Math 115. These are all courses they say people don't need, you know, to do mathematics because everybody had it in high school, that, you know, AB 705, AB 1705 stuff. Yeah, I used to call this algebra lecture, 10 here. Okay. So I have a lecture on how to solve systems in case you guys want to look at that. Like I said, excuse me. Like I said. Yeah, thank you, Juan. Absolutely, you're right. Substitution or elimination. Yeah, pick one of those, you know. Pick one of those things to do. But anyway, in case you guys wanted to look at a lecture of with that stuff. And if I were you, like I said, philosophically, you might say, oh, poor me, I got to do this, right? But as you take more math courses, this is exactly what you have to do. You know, you might have to review a lot of things. And one day you're going to have to review how to integrate even, you know. So you're in the mode of reviewing for a very long time. So anyway, okay. I think what I'll do is I'm going to do the addition method. You might say, what's that? I'm going to multiply equation 2 by 2. So that's a factor now. This is a multiply by 2, multiply by 2. Oh, yeah, it should be a 0, right? Good, thank you. Negative, yeah, thank you so much. And that would have been, here we go. We get 2a plus b is 1, and that's a negative 2a plus, that's going to be what, 8b? That's going to stay 0. So it looks like I'm going to get 9b is what? 1, which means b is 1/9. All righty. B is 1/9. And if b is 1/9, then guess what we can go back and do? Yeah, this is called using back sub. Put back 1/9 in here. And in any of the b's, it doesn't matter which b. So you get 2a plus 1/9 is 1. Or 2a will be 1 minus 1/9. 2a, remember, it's very, replace that with a 9. All right. So let's see what you guys get here. You're going to get 2a is going to be 8/9, I guess. So a will be 8/9 divided by 2. If we divide both sides by 2, a will be 8/9 times 1/2, or simply a will be, looks like a is 4/9. Is that right? Okay. So you have the constants, ladies and gentlemen, a and b now. And so a would be 4/9. Go back here. A is 4/9. And we found b to be 1/9. Okay? So for the most part here, partial fraction decomposition, ladies and gentlemen, gave us the following. Right? This is now going to be 4/9 x plus 4 plus 1/9 2x minus 1. Now remember what this whole thing was about. This was about integrating that original rational function, that was more complicated. Okay, you had a more complicated rational function to integrate. But now, what do you think that gives you? What does that give you? This is going to be what? 4/9 the integral of 1 plus x plus 4 dx plus 1/9 integral 1 over 2x minus 1 dx. Now, here's my claim to you guys, right? Here's the claim for all of this. You say, what's the purpose of all of this? This integral and this integral are supposed to be what? Easier to integrate. These are all easier. And that's the whole idea, ladies and gentlemen. They're actually a lot easier to integrate. So, for both of these are what? U sub, this is a what? U sub, where you have u down here is x plus 4 and then 2x minus 1. Okay, let's not forget the constants. You got 4/9 now, right? Natural log absolute value of x plus 4 plus, do you guys know what happens over here to this one? Right? With u sub, don't you get 1/9 times 1/2? Natural log absolute value 2x plus 1 plus that constant. So your final answer, ladies and gentlemen, is 4/9 natural log absolute value x plus 4 plus 1 over 18th natural log 2x plus 1 plus c. And there you guys go here, right? This is the first integral here, just so you guys can see that. And then this is going to be the second integral answer mixed with that constant, and there it is. So what I want you guys to notice and understand is one thing here, right? If you said in Calculus 2, you know, at this point, what did I show you that was new? Well, assuming you know partial fraction decomposition and how to solve a system, I didn't show you anything new there other than remind you that, you know, when you do this, you can write a more complicated rational function as a sum or difference of simpler rational functions. And then you have this recalling how to integrate with natural log and u sub, right? So it's just putting all these things together to do something more significant, and that's actually a good thing. So, you know, this is why, you know, I said, hey, go back, read and review that, you know, partial fraction decomposition, because this is what you're doing here now, right? But I want to give you guys a note here. Let me show you something that is new for you. I'm going to go back over here. You might look in the book and go back about finding the constants. I'm going to put this as a note. I'm going to call it a by the way. This is kind of new. Sometimes, depending on what you have, right, when you go back to this equation here, some of these problems, your book's not going to use a system to solve for the constants. So back when I took this course, we focused on really solving a system. We had a different book. We had the Anton book, very famous calculus book. But what I want to remark here is this. Take a look here and take a look over here. Right? This is how to find the constants. I'm going to start with this one over here. I'm going to say to you guys, you know what? What happens if x is -4, by the way? Do you guys know what happens if I said to you, let x be -4? Doesn't this portion become 0? Do you guys know what I'm saying? So in the gold, I have x plus 4. If I actually let x be negative 4, I solve for 0 there, and I let that be my x. You know what that means? X is negative 4. So wherever there's an x, I get negative 4 is a 2 times negative 4 minus 1. I know this portion is going to be 0, right? But here's my point to you. I guess that's going to be negative 8 minus 1. Isn't that negative 9? So I get negative 9a. I can divide both sides by negative 9. So a will be negative 4 over negative 9. Here's what I'm saying. What do you get for a? A is 4/9, ladies and gentlemen. Wasn't that what we got earlier for a? Right? So you could take these cases now, right? You could choose, yeah, and 1, that's exactly what we're doing. We're actually choosing a number. In theory, you can choose any number. But you're going to choose a number so that you get a 0 there. You know, you can choose any number for x, and you could create a system. You get an equivalent system. You get a and b's. But we're choosing the specific numbers to 0 those out. Now, you might say, what about this other? What do you do with this now? Well, take a look. If I let x be, what, positive 1/2? Let's go back. If I let x be positive 1/2, doesn't this become 0, this portion here? So that's 0, right? You get rid of that a constant. Because 2x minus 1 is 0. 0 times x is going to be 0. So this is going to be, remember, x is positive 1/2 now. So what you end up with as an equation is 1/2 equals b 1/2 plus 4. 1/2 equals b times 9/2, right? And so b will be 1/2 divided by 9/2, or b will be 1/2 times 2/9. What does that give you for b now? B is 1/9. So you can do this technique as well to get your a and b values. Okay, so that's something your author of the book does. Okay, the author says, you know what? Try it this way. Okay, so you could do either. You could use a system, or you could use those values of x. And there you go, ladies and gentlemen. This is your first partial fraction decomposition kind of question. You know, this is the first one. And these are the cases where you have what's called distinct linear factors. Let me give you another example. X squared plus 2x minus 1. And you say they give me an x cubed minus x. Right? And when you look at the denominator, you might say, hey, this is not distinct linear. They're not different linear factors. You got x cubed minus x. Right? Well, what happens when you factor those terms? You get what? X squared minus 1. X plus 1. X minus 1. Okay, so here's what I'm saying to you. That the rational function that we have to use partial fraction decomposition with, sometimes they don't give you the denominator factored. Sometimes you have to what? Factor it. All right, you guys okay with this? Now, let me say something about how to do this. This is going to be, notice what this is. These are distinct. Distinct meaning different. And these are all linear what? Factors. They're distinct linear. And you go, what do you mean by linear? They're of the form. Your book writes it as ax plus b, by the way. Okay, that's what your book writes, ax plus b. Now, I can write it down somewhere, somehow. Let me double check here. With your book's language. Yeah, I'll write it down this way. You know, so generally speaking, for case 1, distinct linear factors. Okay, generally speaking, this is what your book says to do. It says this, for each. It says something like this, for each factor yeah, of the form. Yeah, that's not it. Let me go back. Let's get that out. See what your book wants to say for distinct linear. I can tell you how I do it, you know, but I want to get the book's version. So if you go back and you look at the book, you go, what are they talking about, right? So this is going to be yeah, 8.4 case, not 4, case 1. Where's your case 1? Yada, yada, yada. What does your book say? Here we go, whatever. For each factor of the form, something like this. A1x plus B1, comma, or times A2x plus B2 times all the way down to AN x plus bn, because in theory you can have n terms there, right? Here's what you're going to write as. They use subscripts. Capital A, A1x plus B1, plus capital A2, A2x plus B2. You're going to write this as a sum, AN over ANX plus BN. Okay? And that's your rational function here. So every one of these terms down here is distinct and linear. Right? Distinct and linear. You're going to have to put what? These constants here. This is kind of what your book says essentially, right? So in this case, if you said, how many distinct factors do I have now? I have 3, is that right? So what this actually means is you're going to write this rational function as A1 over x plus A2 over x plus 1 plus what? A3 over x minus 1, ladies and gentlemen. Okay? Now, personally, I do not use the subscripts A1, A2, A3. You want to know what I use? Just ABC. Okay? Yeah, just ABC. So now you have really A over X plus b over x plus 1 plus c over x minus 1. So again, what do you guys use here? Use algebra, is that right? So you're going to have to add these. And there's no, I would say here for you guys, there's no like, well, I guess I could create a formula, but, you know, you want the LCM. You guys remember that one? LCM is the product of the denominators. X plus 1, x minus 1. So let me actually mark what you get now. This is going to be everything over that LCM. X plus 1, x minus 1. This is a x plus 1, x minus 1. You know how I think of it here for this first term? Right? Which part of the LCM is missing if you have an x down there? The other two. Is that right? The other two are missing. So write it as a x minus 1. And this is going to be b on the next one. bx, what's missing? The x and the x minus 1 is missing from the LCM, right? Plus, and then cx, x plus 1 is missing from the LCM. So now this implies with that logic, right? I don't have space to write down that first rational function, but remember what this implies now. That the numerator here, x squared plus 2x minus 1, this numerator is equivalent to what? That numerator. A x plus 1, x minus 1 plus bx, x minus 1 plus cx, x plus 1. So it implies that my numerators are, in fact, the same here. Okay. Okay. Now, here's what we can do. We can take cases again, right? We don't have to create a system. We can if you guys want, but that would be a 3x3 system. And if you create a 3x3 system, going back to pre-calculus, then you could probably use Gaussian elimination. If you guys remember that stuff. Gaussian elimination from Math 260, because this has three constants, A, B, and C. So we're going to choose this time to use cases. So like for example, here, if I said I want to zero out the A term, if I let x be, I can say let x be 1. Is that right? So if x is 1, doesn't this go away? The A term? And in fact, doesn't the B term go away if I plug in x being 1? So don't forget on the left side, 1 squared plus 2 times 1 minus 1, just by letting x be 1, is c times 1 times 1 plus 1. Okay? So on the left side, I get 1, this will be 2, 3, this will be 2 equals, looks like 2c. Is that right? Which means c will be the number 1. So I have c being 1. I got a constant now. So knowing a constant is pretty good. So what other values of x you guys think I could use to zero out the right side? We tried x as 1 now, right? So yeah, what do you want to do now maybe? Right? We're going to let x now be what maybe? Negative 1 now? So let's see what happens if we let x be negative 1. If x is negative 1, this A term is 0, the C term is 0. Is that right? Right? If you let x be negative 1. But don't forget, you'll have negative 1 squared plus 2 times negative 1 minus 1. And on the other side, you'll get plus what? B times negative 1 minus 1. So you're going to let x be negative 1 everywhere. Okay? You get 1 minus 2 minus 1 becomes b times negative 1. I think it's b times positive 2. Is that true? So it looks like negative 2 is 2b. And what does that mean about b? B is negative 1. Good. So we avoided creating a 3 by 3 system here. Okay? All right. All righty. So now going back again up here. Let's see what x is going to be. Let x be now. What do you want x to be now here? Right? You see this term here? It doesn't matter if it's the b or the c. If I let x be what number? How do I get those things to go away now? 0, yeah. Yeah, exactly. Let x be 0 now. So wherever there's an x, replace it with a 0 here. That's going to 0 out this term. That'll 0 out this term. Okay, so you get 0 squared plus 2 times 0 minus 1 equals, is that a times, what is this? A times 0 plus 1, 0 minus 1. So I get negative 1 becomes negative a. So that looks like here. So negative 1 becomes a negative a. That means a is going to be what? Positive 1, ladies and gentlemen. All right. A is 1, B is negative 1, C is 1. A is 1, B is negative 1, C is 1. We found all those constants. All right, you guys found the constants. Okay, so this is going to be that original rational function. The more complicated rational function was written as the sum or difference of these what? Simpler rational functions. So that implies that the integral is that integral of, well, let me do this. Right? We integrate these. So by properties of integrals, 1 over x dx, and that's going to be minus 1 over x plus 1 dx, plus that integral 1 over x minus 1 dx. Anyway, these over here. See if I can move it over. So now we have integral 1, integral 2. It's kind of funny. Integral 3, maybe a green. Okay, ladies and gentlemen. So now, what are these answers? You guys know? This is going to be natural log absolute value of x for the first one, right? Minus natural log absolute value x plus 1 plus natural log absolute value of x minus 1. So let me write this down, plus a constant, okay? And if you look in back of the book, you might see the following. Absolute value x, x minus 1 over x plus 1 plus c. All right, you guys might see that there. Pretty good, pretty good, pretty good. Okay, now this is distinct linear factors, and this is where you now have what? 2 of them for the price of 1. All right, you guys okay with that? Anybody have any questions on this one here? Right, this is partial fraction decomposition coming back? Do you guys remember that? We got a question? Yeah. Well, be careful. If you, in general, if you do insert any number, you're going to get a system. So if I said to you, I'm going to insert the number 2, right, for x. I go, okay, let's put a 2 there, right? If you put a 2 right in here for this equation here, right? If we put a 2 now, let me go back here. I want to highlight this. This is an important detail. If you put just any number, you're going to get the constants like 2, for example. You're going to get A, B, and C. None of them will zero out. You'll get a number on the left, like 2 squared is 4. It'll be 4 plus 4 is 8, minus 1 is 7. So if you said, oh, I want to use just any number. Yeah, in theory, you could use any number. But that's going to give you the system now. Because you'll have constants A, B, and C. They won't have any zeroing out. So then you might say, well, what do I use so I get zeroing out, right? Go back right here. See this here? See the x plus 1? If you want that to be 0, set that equal to 0, and that means x is going to be what? Negative 1. So that's going to tell you what values of x, right? If you said, oh, what about this one? X minus 1. I want to zero that out. Okay. Then in that case, x minus 1 has to be 0. Then that means x is 1. So you're going to let x be 1. You'll let x be negative 1. So you're going to see these values will zero those terms out, which is what you want. And then you say, well, what if I wanted to zero out the x term, right? Well, let x be what? Just set that equal to 0. So this is what we just did. X is 0, x is 1, x is negative 1. So that's kind of how you go about it, generally speaking. They're very special values of x. So when you have linear factors, they're kind of simple in that way, you know. But as you kick it up, you might say, okay, what happens? What's a kick up? Well, here's a kick up. As you kick it up, you might start to see different things like x squared minus x plus 6. This is over x cubed plus what? 3x dx. So here, again, you look at the denominator, and of course you have to factor. So when you factor, what do you end up with? You factor out the x, and you get what? X squared plus 3. Is that right? Okay, you guys okay with that? Now notice what you have for that denominator now. This here is linear. So you say, okay, good, I know how to deal with that linear term, right? You might say, what do I do with that linear term? We put a over that linear term x. You guys okay with that one? So far, so good? Okay, I'm going to do a kind of a transition for you guys on this one. But I want to point something else out here. What do you guys notice here now? That's not linear. That's a what? Quadratic term. See, you can't factor x squared plus 3. Ideally, you want to factor it completely. When they say factor, you want to factor completely. But you now have a quadratic term. And I'll give you guys a note. If you say, what's a quadratic term? A quadratic term is a term that looks like this, ax squared plus bx plus c. Okay? like a quadratic equation. So they just gave you a quadratic term. Yes, the b value is 0. Yes, the a value is 0. Doesn't matter. It's quadratic, right? So then you say, what do you do for a quadratic term? Here's what your book says. For each quadratic term. And you go, what do you mean each? Yeah, and I guess the book might have it like this. A lot of writing. I don't want to do that, but okay, I guess I have to. A1x squared plus B1x plus C1, right? For each one, they'll give you a product. A2x squared plus B2x plus C2, going all the way down to ANX squared, BNX plus CN. So you have a product of n quadratics, I guess, for each quadratic term, and yes, they are distinct. You introduce the following. Right? This is A1 x squared, B1x plus C1. Okay. This is A2x squared plus B2x plus C2. A3x squared. No, all the way to AN. So let's do that. 3 dots. ANX squared, BNX plus CN. You guys can see that in your book. They're going to say introduce this. A1x plus B1. A2x plus B2. ANX plus BN. These are all linear. Okay? These are now linear. AIX plus BI in some ways, right? This is all in your book, ladies and gentlemen. You can see that there. But if I have only one quadratic, okay, here's what I'm saying. We have only one quadratic. What do you think that means our next term has to be? We put that quadratic, x squared plus 3, but what does the numerator have to be if this is quadratic? There's only one quadratic. This is like a product of n distinct quadratics, right? It's just going to be, you can say, Mr. Judge, can I use A1x plus B1? You could, but you know what I'm going to do? I'm going to say BX plus C. Why do you think I chose BX plus C? I want to stay away from subscripts. But I can't say AX plus B because there's already another A. Is that right? So there's already an A. So ladies and gentlemen, for every distinct quadratic, you're going to do the constant times x plus another constant. Change the letters. Yeah. This is actually, it's a mixed case. You have a linear and a quadratic. So we just introduced quadratic. We're going to start to get to, in some ways, what you can call distinct quadratics. But that'll give you, in theory, 4 equations and 4 unknowns. In theory. So all of this stuff that they give you is all in theory, because like you don't want to have like 10 quadratics, you know. I mean, in theory you can have it, but it's not, you won't see it in a homework question. You won't even see it on a test question because it takes too long. But in theory, this is the process and the approach. So I want to give you what the book says. You go, oh, yeah, you can have n of those? Yeah, in theory, but you're not. You're going to have maybe 1 or 2, you know. So this is kind of how you see that, yeah. But, you know, there's a lot of work here to do this. Anyway, here you go, ladies and gentlemen. And then, what do you think you do now? Do you guys know? You're going to use, what do you think you're going to do with this here, this sum here again? Right? What has been the practice? Yeah, you're going to use algebra, cross multiply. Absolutely. cross multiply. And remember that what that always implies, right? So you don't have to write all this stuff down over and over again. This is what your original what? Function is equivalent to. Right? The original rational function is equivalent. But what you really want to do here, go back up here. Take the numerator, x squared minus x plus 6. Remember, the fractions are equal? So that means my numerators are what? Are equal. So that's a x squared plus 3 plus x bx plus c. So it always means that the numerators are the same here. Okay, so x squared minus x plus c. I'm going to use some algebra. Ax squared plus the 3a plus bx squared plus that cx, looks like. So you get to group these terms, I think. Should we? Or actually, no, you want to leave it like that. All right, because we could do a couple of things here. All right, we're going to leave it like this. Why do you want to leave it like that? You guys remember? If we leave it like that, I guess we're free to take the what? Some cases here. However, adding that quadratic factor just kicks things up. Yeah, I would try to do something like that. Let's see, what happens when x is 0, right? When x is 0, this is 0. So we get 0 squared minus 0 plus 6 is going to give me a times, this is 0, a times 0 squared plus 3. Okay? The x and that b, that's going to be 0 here, right? So you might have said, how do we know x is 0 here? Go back right here. Okay, so what you now get is going to be the statement what? 6 here equals what? 3a, or we know a is the value 2 here. Okay, a is 2. Okay, so far so good. Okay, and I want to give you guys another note, another observation here. I'm going to say this, I'm going to make this statement here, okay? 1 is going to be the same as a plus b. Does anybody know why? Why can I make that statement? A plus b is going to be 1. It's the same. Let me give you guys a hint. You see that 1 there, right? What would happen here? Isn't that going to be, for that first part, ax squared, right? Isn't this bx squared? Right? If we were to start to distribute and do that algebra. Right? What do you guys think? Is that would be okay? If we started to do the algebra, we would see a plus b. Right? Maybe you want to see all the algebra. So this would be plus what? Plus 3a, right? Plus cx. So your right side, let's put this all together. X squared minus x plus 6 becomes, using some algebra, a plus b x squared plus c plus cx plus 3a. Double check that we did some algebra. So this is what I'm saying here, that the a plus b constant is equal to the number 1. Now, why is that a good thing? to know. You know A is what? 2. So 1 is 2 plus B, or what is B going to be? Negative 1. So you have the value of B as well. So you might have to do some algebra. Now this is nice too, because guess what I know what C is? You see C? What is C? Negative 1. So C here is negative 1, ladies and gentlemen. So just doing some algebra after that first. If we only could get one term looking at cases for X, then take it. And typically the quadratics will do that to you. Linear is nice because you can now take cases for X and you'll get some zeros. That's why linear is so good. But when you introduce a quadratic, it complicates things. So 2, negative 1, negative 1. So here's what we get. 2, negative 1, negative 1. I think, okay, A is what? 2, B is negative 1, C is negative 1. I'll say plus negative X. Or actually, you know what you could do? This is minus X plus 1 over X squared plus 3, really. Right? Because this will be, you know, negative X minus C. I can factor out, or minus 1. Right? You factor out that negative 1 term that's there for both. You just put that negative sign there. So maybe, you know, maybe. And then you can say, how do I integrate, right? I get negative 2x dx minus the integral x plus 1 x squared plus 3 dx. Okay? So I'm going to remark here. How can we integrate this? Right? How do we integrate that portion? You know, if you try to do U sub, you're going to have a problem, right? Right? So this is what I'm saying. Here, you might say, I already know this integral. It's 2 natural log absolute value of x. Yes, plus a constant. So that one pops out, right? You know, okay, I like that one. You know what I'm going to say to you guys for this one? That one is the same as x squared plus 3 plus 1 over what? X squared plus 3. Is that right? See, that denominator is dividing what? 2 terms. So we can separate that. We can like distribute division if you want to think of distributing division here. And why is that nice to do? Do you guys see why that's kind of nice? Right? This is x over what? X squared plus 3 plus the integral of 1 over what? X squared plus 3. So that's kind of nice. And then you might say, wait a minute, do you recognize what to do here? U sub, is that right? What would you here be? X squared plus 3. So you notice how some of those integrals start popping out somehow. And then, so you say, okay, what about this one then? Do you recognize this? Yeah, what is that one? is inverse tangent. Is that true? And what is a, though? Square root of 3. Absolutely. So you might say we get 2 natural log absolute value of x, right? This u sub, be careful here. Let me not do all of it here. Let me do something here in purple here, right? This is 1/2 natural log absolute value of x squared plus 3 by u substitution. Is that right? And what is this one, right? This one's going to be 1 over the square root of 3 inverse tangent. This is over x over the square root of 3. All right, you guys okay with that? So all together now, 2 natural log absolute value of x. This is now minus, don't forget, there was a negative sign here. So this is going to be minus all of that, which you just did. 1/2 natural log. I can put this in a parentheses, not an absolute value, because that's always going to be what? Positive. So, like I said before, some of these integrals just pop up. And yeah, plus c. Final answer, 2 natural log absolute value of x minus 1/2 natural log x squared plus 3 minus 1 over the square root of 3 inverse tangent x over square root of 3 plus your constant c. There you go. There it is, ladies and gentlemen. And that's what you get when you start to just introduce a what? Yeah, quadratic. You know? Anyway, let me do this here. Repeat quadratics. This is now just repeat distinct quadratics. Give you an example of what I mean by that. So we have x squared plus x plus 1 over x squared plus 1 squared dx. So this is, well, I'm sorry, that's not, this is what's called repeat quadratics. Right? This is, the first one is when you have a quadratic factor here. So you got some repeat quadratics here. Now you say, what do you mean by a repeat quadratic? Look at the denominator here, right? This is x squared plus 1 times another x squared plus 1. Okay? So here's what I want to say that you do if you have a repeat quadratic factor. So I'm going to put a note here. For each repeat quadratic factor, and it's of the form ax squared. Now this is the nth power, because this is repeat multiplication, right? This is what they mean by repeat. Like in this case, n is only 2. So you're not going to have like, oh, n is 10, you know. You're not going to have stuff like that. You might have just 2. Okay, because you say, why would you do that? Because you're now going to have a bigger and bigger system to solve for constants in general. So in this case, there's only one repeat quadratic factor, right? It's x squared plus 1 to the second power. So there's only one repeat, right? But they're saying for each, you would have to do something like this. You're going to have to write, here's what you do. Start with the first power. Here's your quadratic factor, first power, x squared plus bx plus c. And then ladies and gentlemen. Yeah, and then what you would do really is you increase that power up to, let me do this. I'm going to have to move it out of the way. We need space. So what you're really seeing here is I'm going to raise the powers. This is ax squared plus bx plus c. You raise that to the second power all the way up to the nth power. So if you had a third power, this is kind of what you would do. But they'll use subscripts. a1x plus b1, a2x plus b2. The numerators are all linear, by the way. anx plus bn here. Okay? So this is all in theory. This is partial fraction decomposition theory. For each repeat quadratic, this is repeat, right? Repeat multiplication there. What's the power? This is nth power. What's the power here? 2. Is that right? So here's really what that means if it's power 2. Okay, so let me do it down here. I'm going to copy this. Okay, so here's what you say. You're only going to have 2 terms. X squared plus 1 to the first power, and then up to the second power. There's only 2. The problem you have, though, is ax plus b, and then cx now plus what? Plus d. You got these constants here. Okay, so here's the key. Start with the first power and end with the last power. So if it had the power 3, it would be another term. I don't think you will, though, at all. Again, here we use what? Use algebra. So you'll get ax plus b, x squared plus 1 squared, plus, using that algebra, cx plus d times x squared plus 1. Now remember, what's the whole idea? The numerators are equal. So the whole idea is simply your numerators are the same, ladies and gentlemen. They're the same. All right, this is the equation that you guys have to use here. And then you might look at this and you say, hey, Mr. Judge, what's the deal? I don't think I can zero anything out. You know what I'm saying? Can you see anything to zero out? No. Nothing zeroes out because you can't set the x squared plus 1 equal to 0. You get complex answers. Do you see my point? So on the right side, you're going to use algebra. And I'm going to share with you guys what you get on the right side using all that algebra here by using FOIL and the distributive property, right? At the end of the day, using algebra on all this, you're going to end up with a x cubed plus bx squared plus a plus cx plus a b plus d. After you use all that algebra, FOIL, combine like terms, and then gather these terms here, right? You say what terms? X cubed, x squared, and maybe we want to change colors. gather those terms together. After you use that algebra, because what does this mean here? Do you guys know what this means? This is a lot of good information. If there's no term on the right, on the left side, right? There's no x cubed term. What that means, so you guys can see this here. See these terms? See the x cubed terms? What about the constants? What does it mean about the constants? Yeah, a is 0. That's good to know, ladies and gentlemen. And what does it mean about the b term? B is what? What number's in front of the x squared over here? 1. So that means b is 1. Good. And then that means here, by the way, a plus c is going to be also 1. But if a is 0 already, that means c is what? 1. So it looks like it would have been a hairy kind of system to solve, but now b plus d is 1, but what is b? We already know b is 1, is that right? So I'm looking at the constants down here, this last part. b plus d is 1. Okay? And we know b is 1, so what does that mean about d? Yeah, d has to be 0. Pretty good, pretty good. A is 0, b is 1. So a is 0, b is what? 1. And then, what does it mean? C is 1 and D is 0. So we just have to know how to set this up with partial fractions decomposition. Yeah. X squared plus 1 right in here. Oh, cross multiplication. If I understand the question, this times this gave you that. Okay. So you got, so okay, so we're looking at, well, okay, well, I'm trying to see here. Okay, here's the algebra I'm saying right here, right? Okay, what you would have to do to get the a plus cx, what you would have to do here, you're going to have to use FOIL and FOIL here, combine like terms, and then you're going to get the constant a plus cx using the algebra. So I'm going to say, is there a cx cube? Let me double check here. Let me see if I got ax plus b. There's an x squared plus 1. Well, I'll do the algebra, okay, later. Let's just finish this here. So you have a is 0, b is 1, c is 1, d is 0 here, right? So what do we get now? Did I copy that? Let's paste this. So here's what you end up with, right? You got 1 over x squared plus 1 plus x over what? X plus 1 squared dx. So we're going to integrate this here. So you get 2 integrals. Let's go back. Right? You guys get that there? And then you might say, what do you guys recognize here? What is this going to be? Excuse me. And then what do you guys use here? This is u sub. So by u sub, you're going to end up with -1, 2x squared plus 1. And don't forget plus c. So your final answer is going to be this. All right. And there we go. Okay, now let's talk a little bit about this algebra. All right, I'm going to copy that. Here's what I recommend here. Well, anyway, we'll see that here. I'll do some algebra for you guys and send it to you, but I want to make some remark here. I have an actually meeting to get to, so I have to let you guys go early and not take your break because there's a meeting at 9 here that I have to go to. But I'll send you guys the algebra, you know. I also did something else for you guys. You guys know what I did for you guys? What did I send you guys this weekend? Anybody remember? Yeah, area and what? Volume. Did you guys take a look at that one? For Calculus 2, area, volume? Anybody look at that stuff? Because it was here you go, Calculus 2, area and volume here. So I have a nice video on that you guys were talking about. I have a worksheet that I made for you guys. And I did which ones did I do? I did the odds, is that right? 1, 3, 5, 7, 9 on that worksheet for area and volume for you. This is going to be a long time. But I have the video there too. All right, so some people made that request and said, hey, can I see some of that area and volume? So I did. I took some area and volume there. Yeah. Yeah, it could be. So you want to remember your area and what? Volume. And if you want to look at Calculus 1, I think I sent that to you guys, right? If you want to look at Calculus 1. Now, if you said, I want to see more of these cases. You guys see what I have here? Oops. Can you even see that? Oops. Sorry. You see these partial fraction decomposition? Case 1, case 2, case 3, case 4. What do you think I have there for you guys? Cases for partial fraction decomposition you guys could look over. And I have even some examples. This might be, yeah, some of the same ones I was doing. So I think I'm looking at some of the ones I was doing here. There's 8 pages. Maybe that's what I'm looking at in my lecture notes. But I have those in the lecture notes. I have the video version of them here. So if you guys wanted to take a look at that. And what I was saying to people earlier is that, yes, in the announcements, I have the area and volume, video, and worksheets. So that was a review that people requested. And if you want to see Calculus 1, it's also there. Do you guys remember? I think I showed you guys there. It's also there. So anyway, got to go early. I'll put your homework in Canvas, but I have a meeting at 9, an important meeting. Blah, 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 blah. Horrible stuff. Anyway, print your name, ladies and gentlemen. We'll see you guys later. I'll put homework in and take care.